point out is a bunch of young people. Second, only one of them is wearing a helmet. That's this guy here. Clearly, they've set themselves up to operate in a fairly dangerous domain. They're working against asphalt. They've all got bikes that are going to give them substantial energy. This individual has gained a great deal of potential energy, is now going to convert that into kinetic energy as he comes down. You can see immediately here what he is doing. He's up there, he realizes he's falling, he has begun to respond, he's put his arms up, he's going to bring his arms down to try to control the fall. Classic response, of course. He is certainly going to break his wrist in this particular case, but he's going to come down on asphalt, which is a fairly hard environment. The question is, A, will you get hurt? B, how much will you get hurt? C, where will the injury be? That's what I'm interested in. Okay? So here's my big picture. And I'm going to do this primarily for sports. I'd like to do this for all kinds of things, but sports are where I can get data on humans. So the great thing about sports these days, you take the NFL or the NHL, and I'm going to show you mostly the NHL. We have typically 6 HD video cameras, multiple angles. I see every event. I can do a video reconstruction. I know precisely what the accelerations of the global body were, and in fact of the head in an approximate sense. I can then take that event, I can take the event back to a lab, apply similar accelerations on a dummy, put accelerometers on the head, and obtain local accelerations of the head. I can then take that information, that's my input into a model of the head, to ask what deformations of the head will occur, what deformations of the brain will occur. And then, if I have an injury model, I should be able to predict what the injury would be. So this is my approach. I'm going to take an event. By the way, one very cool thing about this is in the NHL, we actually have some, in the NHL, you're allowed to drive an opposing player into the arena wall. You're allowed to punch a player. You're allowed to drive an opposing player into a post along the side of the arena. And the NHL in Canada has been smart enough that some of these posts are actually instrumented with strain gauges. True. I get a significant amount of data from the NHL partly because the Canadian health system doesn't have the liability concerns that we do. So I can actually acquire it. So we have it. I work with the chair of the safety committee of the NHL, happens to be a person who likes neuroscience and actually works in the area, so we can make some of those connections. Once you know for that event what the local accelerations are, we compute on the basis of a full 3D model. Right now I'm going to show you the 2D slices, where the injury is likely to be, and then we're going to wave our hands a great deal and try to tell you what the loss of cognitive function will be. And we're going to try to compare what that will be, what we think it might be, with what the trainer saw in that event. That's the closest we can come to a true human experiment. Okay? So let's look at this. The first thing to get a handle on, I'm an engineer, I'm a mechanical engineer. I'm going to try to model the head. Well, what length scales am I going to model? This is actually a pretty complicated problem. So let me give you a range of scales here. So protein somewhere down there. Up here is the body. Your typical head, most of you have heads in the range of what, 13, 15 centimeters? So that's sitting somewhere there, and this is really a log scale. So that's sitting somewhere out here. The point here is the loading conditions, the boundary conditions, the accelerations, all of those are only known here. Injury. The particular injury I'm interested in is diffuse axonal injury. Injuries are going to occur somewhere down there. So I have a scaling problem. How do I move information from the large scale to the small scale? So let's think about this. What I'm building is a computational model of traumatic brain injury. It has to be able to run from here to there. This is really difficult to do mechanically. So I have to think about this at 2 levels. At one level, at the organ level here, so I take the brain itself, I build a considered model for the brain tissue, for the entire brain, that includes the anisotropy of the white matter, includes the axonal orientations, or axonal dispersions, or orientation dispersions of the white matter. At the other level, down here, I'm going to look at the cellular mechanisms of axonal injury. We do experiments on single axons to try to decide when functional injury occurs. It's not mechanical injury. Mechanical damage is much later on, but when functional damage occurs. In the interest of time today, I'm not going to talk at all about this. although we have some experiments that I can show you. I'm going to focus entirely on the large scale and then how we track between the two scales. So it's fundamentally a multi-scale problem, and I'm going to show you how we bridge across the scales. So here's a basic hypothesis. We know fairly from a substantial amount of data that shear dominates the AI. Okay? The question is, how does it dominate the AI? So how do we model this? So here's a very basic idea. You say, well, here's the organ. You've got some kind of acceleration. That generates local shear strains. But what you have is an anisotropic material with fiber tracks. And I'm going to then claim, there's entirely a claim at this point, that this leads to primarily stretching of the axons. If the axons are stretched beyond a critical level, I say there is functional damage, and that represents it. So this is the way in which I'm connecting scales. Okay? So it's an inertial loading to the head, but injury is characterized by damage to the neural axons. So here's the model. Here's conceptually how you think about this. I've got the head out here on the left, and I'm sorry, I changed directions on you. So large things are on the left and small things are on the right. In the brain, I know what the tissue structure is, so I've got DTI information that gives me this. Within any given voxel, I define essentially oriented fibers and a dispersion of fibers around the primary orientation. And then, for any one of those elements, I think of that as an axon of the matrix. Now, we all know that there's no such thing as this matrix in the brain, but I'm a mechanical engineer, so I'm going to make big approximations, all right? Now, it turns out that that's not a key approximation. I can show you some sensitivity analysis for it. But conceptually, it helps you to say that what you want to focus on the small scale is the axon.